Let's say we're given a two-dimensional heat equation and our initial condition is given by phi, okay? So this is our initial. And we're also given K, the heat kernel. Here's what we need to prove. We need to prove that our initial condition phi is equal to this expression right here. And at first, this might look a little bit hard, but actually, we only need to prove, here's my claim. It is enough to show that the limit of K at time t is just equal to the Dirac delta function. Now, what is the Dirac delta function? Let's go back to 1 dimensions, okay? Let's go back to 1 dimensions. Let's think about what Dirac delta function of x is. Basically, we start off with integrals. That's 0 everywhere. And the area under this small bit right here, this is 1, okay? So if we take the integral, then the area under the curve is 1, okay? So imagine this, but then the size of this, of the width is shrinking while the height is increasing, okay? So it is getting taller and skinnier. Now, what happens at the limit? At the limit, what we get is, we get 0 everywhere. But at 0, our function is going to be infinitely high, okay? So it has no width, infinite height, and the area is 1, okay? So there's a whole history on the Dirac delta function, and whether it is a function or not, and a physicist made this, and so it took a while for mathematicians to accept it and start using it. But anyway, we're just going to use it. Of course, in the two-dimensional case, this is going to be 0 everywhere, except at 0, it's going to be infinity. And the double integral, because we're in 2 dimensions, is going to be 1, okay? So the volume is 1. Anyway, this is all we need to show. Why? Why is it enough to show this? Because then our limit of K. Okay, so pretend for a moment that we can change the order of the derivative, the integral and the limit. Okay, this is not always true, but for now, let's just assume it's true. This is going to be, by the claim that we showed here, and let me write this in yellow. Okay, this is the claim that we want to show. By the claim, we are going to say that this is equal to delta of r minus r prime. Now we're integrating this over every r prime, right? But it's always 0 unless r prime is equal to r. And it is at this moment when the double integral, if we double integrate the delta function, as I've said before, we get 1, right? So this is going to be phi of r. This is the only r that survives in some sense. And this is how we prove it. Okay, so all we need to do is we need to prove this claim, okay? So here's the proof. First of all, it's easy to show this part, that the limit as t approaches 0 of any non-zero r. Okay, by 0 I mean origin. If r is not the origin, then my claim is that this is going to be 0. Why? Well, what does the kernel even look like? If you look at the problem, K is 1 over 4 pi t e to the negative r squared over 4t. Notice that on the top we have the size of r squared. And because r is not the origin, we know that this is going to be non-zero. So evaluating this limit is basically the same thing as evaluating the limit of 1 over t, e to the negative 1 over t, okay? Obviously, there are constants, but, you know, we're talking about limits, and it's going to be, if this is 0, then the limit of k is going to be 0. Yeah, I hope you can see that. But this is obviously 0, right? Why? From calculus, we have, I'm going to bring the negative exponent down. Notice this t, the first t right here, is trying to go to 0, but the second t is an exponential, right? So this guy always wins. I'm not going to do this thoroughly, but we can use L'Hopital's rule to show that, in fact, the denominator goes to infinity, and therefore the whole limit goes to 0, right? Okay, we still have a long way to go. The second part, we have to integrate k. Okay, and what do we hope to get? We hope to get 1. Here's what we want to show next. So, want to show. Okay, so what is the double integral over the whole plane of the definition of k? E to the negative. And I'm going to write out r, the absolute value of r squared, as x squared plus y squared, okay? Because that's exactly what that means. Over 4t. Oh, sorry, it's not dt, it's dy dx, right? Well, let's use a change of variables, okay? So let's say that, what should we do? What should we use as a change of variables? Maybe we can let p equal x over square root of 4t, and then q equal y over that, so that our bounds are the same, but we get e to the negative p squared plus q squared. So that simplified a lot. But then we have to find dp as well as dq, but that would be 1 over 4t, right? So that cancels with the 1 over 4t over there, and all we have left is 1 over pi, right? Okay, now let's change this one more time into polar coordinates, okay? So this is going to be equal to, I'm going to leave 1 over pi out here. So instead of negative infinity to positive infinity, I'm going to do our radius going from 0 to infinity and our theta going from 0 to 2 pi. Okay, and we'll have e to the negative r squared, and our determinant of change of coordinates will be r. Hopefully you remember this from calculus class. And we have dr d theta. And if we calculate this out, this part is actually just going to be pi. Should I do it for you? Well, let's see. We'll have to do one more change of variables if we want to make this perfectly clear. If we let u equal negative r squared, then du will be negative 2r dr, right? So this is equal to 1 over pi. Our theta stays the same. But now we have e to the u du d theta, and our u goes from, see, when r is 0, we're still at 0, and when r is at infinity, we're at negative infinity. Sorry, theta doesn't go from 0 to infinity, it goes from 0 to 2 pi. Notice that we can separate the integrals out, right? So we get 1 over pi, and then the theta integral turns out to be 2 pi. But the EU integral, if we integrate e to the u, then that's just e to the u, and we're plugging in negative infinity and 0. So that will be, am I missing a negative? Yeah, I'm missing a negative. The negative comes from here, so we'll have negative. Anyway, if we plug in negative infinity, we'll get 0. If we plug in 0, we'll get 1. And therefore, this is going to be, okay, what else am I missing? Okay, here's what I'm missing. I'm missing, when I substituted dr for du, I was actually, here's what I'll write in red. I was missing negative 2. All I wrote was negative, but I should have written 2 down here, right? So all of this gets multiplied by negative 1. Sorry about the mistake. And we'll get 1. So the double integral of k is 1 as desired. And therefore we can claim, this proves the claim that the limit of k is the delta function. And we have shown earlier that this proves the original statement. Okay, so now we are done.